All right, guys. Any one question that you need me to talk about? Which one was the hardest question on the quiz? There are versions, so I don't know what the last one means. The clock one. You guys get the clock problem? Think so? So, yeah, not much change between the versions on the clock problem, but you got something like the minute, a clock, the time is changing from like 3 to 3:25 or something like that, and it wanted you to figure out the angle that the minute hand rotates through. So your minute hand's going to be straight up on the hour, and then it's going to be down here-ish after 25 minutes. Right? So maybe this was 3 and this was 3:25. How do you figure out the angle that it rotates through? Now, you could guess, but let's not do that. That's BS. No one cares about that. How would you logically figure this out?
Divide 30.
Yeah, you can divide. I would, personally, when I think about this, I take my half circle, which I know is pi, and I divide it up into 5-minute segments because I landed on a 5-minute interval. Right? So I could break this up into 5, 10, 15, 20, 25, 30. So what's happening is I'm going 1, 2, 3, 4, 5 out of 6 segments or sectors. So if you go 5 out of 6 sectors, the angle is going to be 5 pi over 6. The answers were all negative. Why was it negative?
Because it's clockwise.
Because, yeah, technically you're going clockwise, which is a negative angle measure. So, we talked about angles and how to graph angles. What I want to do today in this section is define the 6 trig functions. Okay, so the whole point of this class is to study 6 new functions. And all of them have to do with right triangles. Okay? One thing that, well, there's a couple things we got to get straight before we get into this. All right? So let me talk about the intro here. If you have a right triangle, and you label one of the angles theta, okay, it's whatever it is, I don't know what it is. What we're trying to do with our trig functions is measure the shape of this triangle, not necessarily the size. So what I mean is, as this angle changes, the shape of the right triangle will change. So if I make a bigger angle right here, this is a taller and skinnier right triangle than this guy. But the size is not dependent on this angle. What I mean is, I can cut this right triangle off right here. Right, here's another right triangle that has the exact same angle, but a different size. So the idea with trig functions is we're going to try to build some functions, some formulas that help us measure the shape of the triangle, but not necessarily the size. The way these functions work is angles are going to be the input. So these are like the x values for your function. This is what you input. Maybe it'll be a 45-degree angle, so you input 45 degrees to your function. Maybe it'll be pi over 7 or something. Okay, angles are the input of these functions. And then the output is going to be a ratio of side lengths. Okay, so for example, if this side length here is A and this side length here is B, then an output of a trig function would be something like A over B. It's a ratio. So all trig functions have an angle for input and a ratio for output. Now, I'm going to define what each of the trig functions is, but before that I need to get some terminology straight. Depending on where you choose to put this angle, we have different names for the sides. So, sort of talking about this remark about terminology here. So here's a right triangle. if I choose to focus on this acute angle here, this is the one I just want to look at and consider. I'm not even thinking about this one. I'm just looking at this one. Then I have convenient names for all the side lengths. This side length always has the same name. What's this side length called? Hypotenuse. No matter what, the side length that's across from the right angle will be the hypotenuse. Now these two sides can be labeled independents on this angle. So for example, this side length is opposite of this angle, right? It doesn't touch it. So this side length can be labeled opposite, meaning that it's opposite from the angle we're focusing on. This side length here is touching this angle, so we're going to call it adjacent. Or if you're a lazy mathematician, this is hypotenuse, opposite, this is adjacent. What you'll notice, so this is if you're referencing this green theta here. But I can draw the exact same triangle, but choose instead to focus on this angle. What does that change with my labelings? Will this still be opposite here? No, this is now adjacent. Okay, so one thing to keep in mind is if you change the angle you're focusing on, these names change. And then your definitions for the trig functions are all going to be a little different. So if we're focusing on this angle, then this side down here is opposite. If this side touching the angle is adjacent, the hypotenuse doesn't change. So here's your definitions for the 6 new functions that make up, I would say, 90% of this class. Okay, these are the 6 things we'll be studying from here on out. Let me go over them a little bit, and then we'll do some examples. So, 6 trigonometric functions of the angle theta are defined as. So all of these are in reference to a right triangle. So in order to make any sense of these definitions, you have to have a right triangle. Okay? Later, we're going to try to define these without a right triangle, but for now, all of these depend on a right triangle. So when I say sine of theta is equal to opposite over adjacent, opposite over hypotenuse. Okay. What that means is, first of all, sine is the function. This is the new function that I just made up that's going to help me measure something about a right triangle. So this is like your f, your function. This is not multiplication. Okay, this is of function notation. F of x, sine of theta. Okay, so this is the input. This is like your x. Equals this ratio. So this output is like your y value. In order to make any sense out of this, you have to have a right triangle. If you don't have a right triangle right now, this doesn't make sense. But what it's saying is in this right triangle over here, sine of this angle theta is equal to whatever this number is over whatever this number is. And you go on and you can pick combinations, right? You can choose any two of the sides and get a new trig function. Right? So underneath it I wrote cos theta. Cos theta switches to adjacent over hypotenuse. Tan theta is opposite over hypotenuse. Oops, opposite over adjacent. Where my head is. So with these three, I've actually already chosen all the possible combinations of sides. Right? Sine, use these two. This first function, sine, use those two sides. Cosine, use these two sides. And then tangent, use these two sides. So I've picked every possible combination of sides that I can have, and I've used them to define these three functions. But you'll notice there's three other functions on the other side. These are called the reciprocal functions. They use all the exact same side lengths, but they flip the ratios. They're not super they're not super important because anything you can do with one, you can do with the other. Right? Anything I can do with sine, for example, I can do with cosine. Okay? But we do want you to get used to them. We do want you to study them. So let me write these real quick. So this CSC function, this is pronounced cosecant. And all it is the reciprocal of sine. It's what you get if you flip this ratio. The reciprocal of cosine is called secant. Secant of theta is what you get if you flip this ratio. And then tangent of theta, the reciprocal is called cotangent of theta. And you flip this ratio. So these are your six trig functions. Are you going to have to memorize these definitions? Yes, absolutely, 1,000%. No doubt. No doubt at all. You are going to have to know these. Some people use the acronym SOHCAHTOA, or the mnemonic device, I guess I should say. They just remember the word SOHCAHTOA. And what it tells you is that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So it helps give you a way to remember the first three definitions. Right? Once you have the first three definitions, right, sine opposite over hypotenuse, you can get cosecant by flipping it. Okay? So the two things you really have to remember, you have to remember what sine, cosine, and tangent are, which you can do with this. But then you also have to remember how they match up. Okay? Sine matches up with cosecant. Cosecant is the reciprocal of sine. I don't know how you want to remember that. Different people have different ways of remembering it. Personally, I'm a very pessimistic person. Okay, so I'm always thinking that life is hard. So to me, I know that sine doesn't match up with secant because they both have an S, and that would be too easy, right? That's just, math is never that nice. So sine has to match up with cosecant because they have different starting letters. That's just how I do it. Tangent and cotangent are easy, right? Tangent and cotangent match up because they both have tangent in them. But these you have to swap. So you will have to memorize this. And one thing that I notice, depending on how your brain works, some people will get cosine and cotangent mixed up. They're totally different functions. The full name is totally different. Cosine, cotangent. But if you look at them, they're just off by one letter. And so sometimes people will read cos, but they'll think cotangent for whatever reason. All right, so you got to be pretty meticulous when you're studying these things. Let me try to give you an idea of what we can do with these things. The first couple examples are not going to be super mind-blowing. Okay, the first couple examples are designed to get you used to these definitions. Eventually, we'll get to a point where maybe you can see how you can use these in applications. So let's run through some examples. So in the first example here, I gave you a right triangle. 3, 4, 5 right triangles. That was even nice. I did all the side lines. I put theta over here. And I said, find the values of the 6 trig functions of theta. What am I asking you to do, and how do you do it? Find all this. I'm asking you to find all this. I'm asking you to take this new function, sine of theta, which you have no intuition about yet, right, and figure out what it equals for this triangle. So this is really just to make sure you can apply this definition. So sine of theta is going to equal forever and always opposite over hypotenuse, which in this particular case, how do we figure it out? You got to know which side's the opposite side and which side's the hypotenuse. That's about it. But that comes from the angle. Theta's here, so this is the opposite side. Right? This is the adjacent side, which I'll label for later. This is the hypotenuse. So sine of theta in this case is 4/5. Some of you are going to be, I'm sure some of you are already thinking, what does this mean? I'll try to talk about what the 4/5 means in a second, but let's go ahead and get all the other ones done real quick. What's cos theta for this particular triangle? Cosine is always adjacent over hypotenuse, and for this particular triangle, that's 3/5. Tangent of theta is always opposite over adjacent, and for this particular right triangle, that means 4/3. And then you do the reciprocals. Once you find sine, cosine, and tangent, then you can do pretty quickly cosecant, secant, and cotangent. For these three, you just flip this one, right? So for cosecant, you flip sine. For secant, you flip cosine. And for cotangent, you flip tan. So these are your 6 trig functions for this angle theta. Let me stop talking for a minute and ask you how that feels. Scary? No? Fun? Boring? A little bit. 2 strange things. Let me start with one strange thing. This is not the way functions usually work. Okay, usually I give you a function f of x equals x squared, say. And then I ask you what's f of 2. And you plug 2 into x squared and you get some output. Okay? I have not given you what the value of this angle is. Right? So your input is a variable in this case. It's a variable because I don't know what this angle is. I don't. But I don't need to know this angle to get my trig functions as long as I have a right triangle. There are only certain angles that we can actually calculate trig functions for easily. There has to be some sort of nice structure to the right triangle in order to be able to, the angle has to give you a right triangle that has nice structure, like something like 45 degrees will give you something very nice. You can calculate sine and cosine for that. But for most, if you just pick a random degree measure, 19 degrees, sine of 19 degrees is not something I could calculate without a calculator. And I'd be approximating. So most angles give you terrible decimals, irrational numbers for outputs. So a lot of times we won't even write the angle just because we don't even know what it is. All we know is what the triangle is. Other than that, what do you think? I can't give you a lot of intuition all at once, but let me focus on sine for a minute. This number that you get out over here for sine, is it ever going to be bigger than 1? So in order for this number to be bigger than 1, the top would have to be bigger than the bottom. Right? Numbers that are bigger than 1 have a bigger numerator than a denominator. So is it ever possible for sine to be bigger than 1?
No.
Why not?
Because the hypotenuse is the longest.
Hypotenuse is the longest side in the right triangle. Right? So the bottom's always going to be bigger, so it's always less than 1. it's always greater than 0 for a right triangle, not in general, but for a right triangle, sine is always greater than 0 because the smallest this opposite side can be is 0. Right? We're not talking about negative opposite sides right now. So here's my question to you to help give you an idea of what this means. If I tell you that sine of theta is really close to 1, right? Or I tell you that sine of theta is really close to 0, what do you think that means about the corresponding right triangle?
It's as big as the hypotenuse almost.
Right, so when it's 1, that means the opposite is almost the same as the hypotenuse. And when it's 0, that means that the opposite is super close to 0. So this triangle would be a really tall triangle, something like this. Right, because whatever this length is pretty close to this length. Okay, and the taller your triangle gets, the closer you're going to get to 1. This guy would be really short. This is getting closer to 0. And then as you range from 0 to 1, you kind of get taller and taller triangles. So sine measures the height of the triangle versus the hypotenuse. And when that ratio gets closer to 1, you're getting closer and closer to a straight vertical triangle. And when that ratio gets close to 0, you're getting closer and closer to a horizontal line. Kind of a way you can start building your intuitions for what sine and cosine mean. What about, one more question on here. What do you think happens if tangent of theta equals 1? What's that?
What sides are you saying?
Which side?
The opposite and the adjacent.
So the opposite and the, because tangent is opposite over adjacent, if tangent is 1, then this is the case where you have a triangle that has exactly the same side lengths, an isosceles triangle, isosceles right triangle. Okay, the only way tangent can be 1 is if you have an isosceles right triangle. Then as tangent starts getting bigger than 1, that means that the opposite side is getting bigger than the adjacent side, so it's getting taller. And as tangent starts getting less than 1, this opposite side is getting shorter. So these are not instantly accessible, what they mean. Okay, but as you work with them, you'll start to build an intuition about what these trig functions might mean. So any questions before I continue? Okay. I'm going to look this up here because it's so crucial. And that's a life or death statement. So, the next example is of the same type. Okay? But I've given you a little less information. It says for the triangle below, find the values of the 6 trig functions of theta. But I only gave you 2 side lengths. I gave you 8 and 17. So that's going to make it hard to find sine because sine is opposite over hypotenuse, for example. I don't have opposite. Uh-oh. What do you do?
Subtract the side from the hypotenuse.
Right, so not subtract them directly. You have to apply the Pythagorean theorem. Right? For a right triangle, I know that a squared plus b squared equals c squared, always and forever. Right? So maybe you label this a, this b, and this c. And the Pythagorean theorem tells you a squared plus b squared equals c squared. You know a, you don't know b, you know c. So plug it in. 64 plus b squared equals 289, right, if you calculate all these squares. Subtract the 64 over to the other side, and you'll get b squared equals 225. So b is equal to plus or minus the square root of 15. Remember, when you square root both, oh, not the square root of 15, sorry, just 15. Right, when you square root both sides, you usually get a plus or minus. That's how you solve equations with the square root property. Do I really need a plus or minus in this case? No, because it's the length of a triangle side, you can disregard the minus. Okay? Technically speaking, as far as algebra is concerned, you should have a plus or minus, but in the context of the problem, the minus is silly. So this side length here is 15. What's going to happen as we go through this class is you're going to have to do the Pythagorean theorem constantly, all the time. It's just because we do so much with right triangles, it just happens. So what I will do to save myself time in front of the class, I will probably jump straight from here to here without any of this work. Assuming that if I say you use the Pythagorean theorem, you guys can figure it out on your own. Okay? So I'm going to try not to waste a lot of time with these Pythagorean theorem calculations. If you're having trouble with it, figure out what the problem is now, because it's not going away. You're going to have to do this like in your sleep. Now we can fill out, now we can actually answer the question, but we had to figure out this missing side first. So if I want my 6 trig functions of theta, I now label opposite, adjacent, hypotenuse. I go to town. Town is my favorite place to be. All right, these are the sort of standard 3 trig functions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So when I fill these out, I'm just going to do what I'm told to do here, opposite over hypotenuse, 15 over 7. Adjacent over hypotenuse, 8 over 7. Opposite over adjacent. So at this point, it's all memorization. If you can memorize these definitions, you're good to go. Of course, that's only half the work. Well, half the functions. How do I get the other 3? Flip, right? Reciprocals. So the only thing now to remember is what is the reciprocal of sine? Cosecant. So that makes secant the reciprocal of cosine and cotangent the reciprocal of tangent. So this will be 17 over 15, 17 over 8. So those are my 6 values of the trig. So those are good. Questions?
What does CSC stand for?
Cosecant. Cosecant. There's a special relationship between sine and cosine, and secant and cosecant, and tangent and cotangent. Okay, those co's are not they're not random. Okay, this is sine. This is cosine. These are called cofunctions. I know, real original. There's 3 pairs of cofunctions, sine and cosine, secant and cosecant, tangent and cotangent. I will basically, well, I'll tell you what the relationship is between the cofunctions in a moment. Okay, I got a little blurb about that down below. But these guys, the cofunctions, are all related in a sort of tricky way. But before I get to that, let me now talk about, so now that you're used to these definitions, let me actually talk about how we might be able to replace this with an actual angle. Okay, so I want to be able to put a 45 degrees in here, for example, and figure out what sine is. Right, I want to be able to put a 30 degrees in here and figure out what sine and cosine there's only, right now, 3 angles that we can easily figure out all the trig functions for. So there's 3 special angles. And these 3 special angles are going to come up again and again and again and again and again and some more. The 3 special angles are 30 degrees, 45 degrees if I'm going in order, and 60 degrees. That's in degrees. What do these correspond to? What are the radian measures here? This guy's pi over 6. This guy's pi over 4. And pi over 3. So these are the special angles in degrees, and this is what you would get if you convert to radians. Remember, if you're not sure where I got this from, to convert to radians, you multiply by pi over 180. So if you multiply by pi over 180, you will reduce to pi over 60. So what I want to do, if you look, the first example, I want to figure out what sine of 45 and cosine of 45 is. These are the only easily accessible angles that I can find sine and cosine and tangent. Anything else, 61 degrees, 62 degrees, way too much work to figure out what that is right now. So let's start with 45 and see if we can figure out what sine and cosine has to be. The idea is to figure out, to determine what sine of 45 is, you have to have a right triangle with a 45-degree angle. Right? That's what all of these definitions refer to, some right triangle. So let me draw you a representation here. So a right triangle with a 45-degree angle here. So I know it's not quite to scale, but pretend. If I had a right triangle with a 45-degree angle here, and I knew all the side lengths, then I could figure out what these are. So my first question is, if this is a right triangle and this is 45 degrees, what is this? 45 degrees, why? You only got 180 to work with, right? In in any triangle, you only have 180 degrees altogether. So this is 45, or this is 90, so you knocked off 90 of them, you knock off another 45, all you have left is 45. Okay, so now we need the tiniest bit of geometry. If you have these two opposite angles the same measure, what can you say about these side lengths? They're the same. Okay, if these base angles are the same, then you have an isosceles triangle. So these are the same. Now remember what I said about size versus shape. Trig functions don't care about size. So whether I choose to make this a really big 45-45 right triangle, or I choose to make it a really small one, the trig function should give me the same thing. So what I'm going to do is choose this single side length here to be 1. If I choose it to be 2 or 5 or 7 or pi, I'll get all the same answers. Because trig functions don't care about size. They only care about shape. And I can show you the calculation if we choose a different number, but let's start with 1. If this is 1, what is this? 1. This is 1 and this is 1. What is this?
Just say 2. 1 by 5.
What is it?
1 by 5.
No, 1.5. What do you have to do? Do the Pythagorean theorem. A squared plus b squared equals c squared. 1 squared plus 1 squared equals c squared. So 1 plus 1, 2 equals c squared. So c is equal to root 2. Plus or minus, but we're just going to take the positive because it's a triangle. It's an actual side length. So once we pick this and this is determined. And now we can calculate our values. So this guy, because these are both 45, it doesn't matter which angle you focus on, because it's going to be exactly the same. But say we focus on this angle. Then this guy will be opposite. This guy will be adjacent. This guy will be hypotenuse. So I asked for sine of 45 and cosine of 45. What are they? Sine of 45 is opposite over hypotenuse 1 over root 2. Cosine of 45 is adjacent over hypotenuse. Adjacent over hypotenuse 1 over root 2. Unfortunately, this is not usually the way you will see sine of 45 written. Usually, in most books, they're going to rationalize the denominator. Do you remember what that means?
Take out the square root.
Get that square root out of the denominator. How do you do that?
Times it by the square root over 2 or square root.
Right, multiply top and bottom by the same thing, like this. If you multiply top and bottom by root 2, you will get root 2 on top, because 1 times root 2 is root 2. 2 on the bottom, root 2, or root times itself gets rid of the root. Same thing will happen over here if you get rid of that root in the bottom. In 90%, 95% of the problems you do for me, I'm going to want you to rationalize the denominator and make it look pretty. Later in life, maybe it won't be so important, but for me right now, just so we all answer the same thing when I say what's sine of 45, we're going to stick with the rationalized denominator version. So, questions? Okay. I'm going to draw this up here. So this is the right triangle I used. It was 1, 1, root 2. And it led me really quickly to see that sine of 45 degrees was equal to 1 over root 2. Then we rationalized just to make it pretty, but this you could read off really quickly. And it also gave me this. What happens, do you think, if I change this 1 to, I don't know, 5? What if I would have picked 5 for this side length to begin with? Does that change anything? What's this side length become? 5. What do you think this becomes? It's going to be 5 root 2. Okay. You could check. Right, you'd have to do 5 squared plus 5 squared equals c squared. 25 plus 25, 50 equals c squared. Square root. But you can pull a 25, you can simplify this to 5 root 2. So then if you do opposite over hypotenuse, right, if you go and you do 5 opposite 5 over hypotenuse, 5 root 2, 5's cancel and you get the same thing, 1 over root 2. Okay, so the size doesn't matter. We did it with 1s. If you did it with 5s, this is what you do, which is the same. Okay. What about tangent? What's tangent of 45 degrees? 1. Why?
Because it's the opposite over adjacent.
I have a triangle with a 45-degree angle, so do opposite over adjacent. Tangent is opposite over adjacent. Let me say something else. Oh, what's sine of pi over 4?
Square root of 2 over 2.
Root 2 over 2. Why?
Because it's the same thing over here.
Because pi over 4 is 45 degrees. It's the same exact triangle. Most of the time you'll see, well, I don't know about, yeah, most of the time you'll see radians rather than degrees. So get used to this correspondence here. All right, instead of writing 45, I could have just as easily written pi over 4. So over here in this triangle that I'm keeping for you for notes, this is either a 45-45 right triangle or it's a pi over 4 right triangle, which would change these angles to pi over 4s. So sine of pi over 4 is the same thing. Cosine of pi over 4. Good? So I didn't write it here because I wrote it over there, but sine of pi over 4 root 2 over 2. So the other example I wanted to do, which is actually slightly trickier, is for the other special angles. So the other special angles are 30 and 60. Let me do 30 first. So if you look at the next example, it says find sine of 30 degrees and cosine of 30 degrees. Okay. What do I need to figure out what the sine of 30 degrees is? A right triangle. To do any trig function right now, to figure out the value of any trig function, you need a right triangle. So let me start by drawing a right triangle. Here's a 30-degree angle. Unfortunately, if this is 30, this is not 30 as well, right? What's this over here? 60, because again, this is 90, and they have to add up to 180. So you have 60 degrees left over here. So it's not quite as straightforward how these side lengths relate. The trick to actually figure out what these side lengths are is to reflect. It's kind of funny. What I mean is draw the exact same triangle down here. All right, so draw another triangle right underneath, another right triangle that has the same angle measures. So just imagine you took a piece of paper and flipped this down. What would this angle be right here? 30 degrees, because it's the exact same triangle. And what would this angle be down here? 60 degrees. Okay, so now check out what we have. This big angle is what? 60 degrees. So we have a 60 degree, 60 degree, 60 degree. So if you focus on this big triangle right here, it's equilateral. Okay. So we can use that. In this case, I'm going to signify, I'm going to pick the first side to be 1, but this is the side I want to be length 1. Right? Remember, my original triangle was this 30, 60, 90, so I'm picking 1 right here. Let me redraw my original so you know what's going on. This was my original triangle. And I'm saying let's pick this side to be 1. Now referring to this figure, what do you think this length is down here? 1, because it's a reflection. It's the same exact triangle. So this guy's going to be 1. Now because this is an equilateral triangle, what's this side length here? Right? Because this whole side is 2, so this whole side has to be 2. Which means over here on my triangle that I started with, I have a 2. And then what about this remaining side length that I care about here? Pythagorean theorem. You got a right triangle, you know 2 of the sides, do the Pythagorean theorem. So maybe we call this A, B, C, or whatever you want to label it. A squared plus B squared should equal C squared. A squared I don't know, B squared is 1. C squared is 4. If you isolate A, it'll be root 3. All right, subtract the 1 and square root. So this extra triangle that I dropped below doesn't have anything to do with anything except that it helps me get this 2. It helps me understand why this side is double this side. That's it. After that, then I can get the third side using the Pythagorean theorem. Okay, so this triangle has 1, 2, root 3. Now, because I asked you for sine of 30, I'm going to focus on this 30-degree angle, label this the opposite side, this the adjacent side, and this the hypotenuse. So what's sine of 30? Sine of 30 degrees is opposite over hypotenuse, 1/2. Cosine of 30 degrees?
Root 3.
Root 3 over 2, adjacent over hypotenuse. And if you want to do the radian counterpart, this would tell you that sine of pi over 6 is also equal to 1/2, because pi over 6 and 30 are the same thing. Cosine of pi over 6 is also equal to root 3 over 2. And because pi over 6 and 30 are the same. So let me log this information over here. Right triangle, 30-degree angle, 60 degrees over here. The way you always label a 30-60 right triangle, the shortest side is 1, the hypotenuse is 2, and the leftover side is root 3. Once you have that triangle labeled, then you know exactly what sine of 30 and cosine of 30 are. 1/2. Of course, instead of 30 degrees, you may think of this as pi over 6, and instead of 60 degrees, you can think of this as pi over 3. So you can replace this with pi over 6, and you'll get cos pi over 6 sine pi over 6. We've done all of our work. What about, well, questions? Let me stop, say, what about this is confusing?
I just have one question.
Yeah.
So I get how to what sine and everything is, but what are they actually used for? Like, what are the actual values? Like, I think you explained it. I know they're the sides, but how is it used for?
So as far as uses go, we'll do a whole chapter on applications, but as far as immediate uses of this go, your whole world is made up of triangles. Every shape in the world, every polygon in the world is a bunch of triangles put together. Okay? So even a circle is a limit of triangles. But for example, if you want to find the height of a building, maybe it's easier to calculate this angle here than actually measure the height of this building. And so if you can calculate this angle, and you can measure, just by walking or using some instrument to measure that this is 20 feet, then you can set up a trig function argument to get the height of the building. So what it'll do is in the case when an angle is easier to measure than a length, you can use that angle to get the length. For example, this guy, if I wanted to solve for this x here, I would use which trig function, Tangent, why? Yes, right, because I know adjacent, if you focus on this triangle here, I know adjacent, I'm looking for opposite, I know 60, so I can set up the argument, tangent of 60 has to equal opposite over adjacent. And then I know I can calculate tangent of 60, I haven't gotten to that yet, but I can, so then I can solve for x. So that's one straightforward use of this. There's a lot. Yeah. Question?
More of something related to it though, instead of a question. Isn't that how someone a long time ago calculated the circumference of the Earth? They like measured the distance from a mountain and then the degree it's at and how it changed. It's something that reminded me.
I have never heard of that, but I believe it.
Okay.
If you have
Someone
like
figured
a,
out the height of the mountain and how far away it is and how it changed depending on how close or far you got. That's how he figured out the circumference of the Earth pretty
oh,
accurately.
that's cool. That's cool. I don't know. I never heard that.
I'll have to figure what the guy's name was.
Okay. I have 5 more minutes, so let me finish up with this idea of cofunctions and you know, sine of 60 and cos of 60. Because once you have sine of 30 and cos of 30, sine of 60 and cos of 60 is really easy. Right, basically, once you have this triangle, you can use it to get sine of 60 and cos of 60. How do you do it?
You switch the opposite.
Focus on the angle 60 degrees instead of 30 degrees. So if I want you to find sine 60, cos 60, both of them, you would use this triangle again, 30 degrees, 60 degrees, right triangle, and you would use the same side lengths, 1, 2, root 3, but now you focus on this 60-degree angle here. So this becomes opposite. This becomes adjacent. And this becomes, well, this stays hypotenuse. So what happens is sine of 60 equals root 3 over 2. And cosine of 60 equals adjacent over hypotenuse 1. So well, does that make sense? So this triangle encodes both all the trig function values for 30 degrees and all the trig function values for 60 degrees. And one thing you might notice if you're astute, the sine of 60 degrees and the cosine of 30 degrees are the same. And the cosine of 60 degrees and the sine of 30 degrees are the same. So the general statement here is that when you take a cofunction, see how sine and cosine are cofunctions? And you plug in complementary angles. What are complementary angles? Angles that add up to 90. Supplementary add up to 180. Complementary add up to 90. So if you take sine of 60, it'll be equal to cosine of whatever you get, whatever's left over out of 90. Okay, so in this case, out of 90, if you take away 60, you have 30 left over. More generally, I've written the most general statement up there, but just so you have sort of an idea of what I'm talking about, sine of 18 degrees, right, using this cofunction idea, should be equal to cosine of what? 72 degrees, the leftover out of 90. And it's true for any pair of cofunctions. So tangent of 32 degrees should be equal to what? Put a co in front of this. So instead of tangent, change it to cotangent. And instead of 32, 8. So all cofunctions are equal if the angles add up to 90. Tangent of 32 is not equal to cotangent of 32. That's BS, garbage, wrong. Okay? But tangent of 32 is equal to cotangent of 58. Okay, so you have to change the angle. You can't keep the angles the same. These don't even think about that. The angles have to change. Okay, so you can definitely do your homework from 8.1 now and more. All right? I I started, I think, some of 6.2. I started some of 6.2, so maybe you can try that. Do what you can, and we'll talk again on Monday.